So we're doing S2 Edexcel International Jan 2017. The first question is, some of my students might say it's a trick question. I don't know if I don't regard it as such. We should all know that the probability of getting one particular value on a continuous distribution, because normal continuous is 0. To get we're looking for a range of values for a continuous distribution, so it's 0. That's it. Let's move on. The discrete random variable x has a binomial distribution 20, 0.5. Find probability that x equals to 8. You can use tables, but it's only one single value, so I don't really want to use tables. We can use the formula. That's 20C8 times by the probability of 8 occurrences times by the probability of it not occurring 12 times, because there's 20 occurrences in total. And that gives, if we work that out, that gives us an answer of 0.162 to 3 significant figures. Always give at least 3 significant figures in exams, certainly in stats exams. Find the probability that x lies within one standard deviation of its mean. Right, well, it's a binomial, and we know the mean of a binomial is equal to NP. So that means it's equal to 20 times 0.45, which is equal to 9. Now the standard deviation squared, in other words the variance, is NP 1 minus P. So that's 20 times 0.45 times 0.55. And that comes to 4.95. But that's the variance, so the standard deviation is the square root of that. Okay, so we want to know that it lies within one standard deviation of the mean. So that's 9. So we want to find a probability. Let's work out the square root of 4.95 first. That's 2.22 or 2.2. Right, so that's a probability that it lies between 9 minus 2.2 and 9 plus 2.2. But here's the thing, this is a discrete distribution now. So in order for this obviously comes to some number, 6.8 or just slightly below 6.8 when you work the exact. But the point is it's discrete, it can't be 6.8, it needs to take a whole number. So that's 7 x, and that is, this comes to 11.2, but it can't take the value 11.2, so that's the same as 7 to 11. Okay, so we can use the tables with 20 and 0.5. They are in the binomial tables. So that's equal to 1, not 1 minus, it's a probability that x is less than or equal to 11. Take away, that would give us all the values including 6, 5, 4, 3, 2, 1, 0. So we need to take those values away. So it's 6. So now let's look for these numbers on the table. So here's the tables, 0.45 is the second to last column. We want 20. So the probability, we're looking for the 11, that's 0.8692. Take away the 6, which is 0.1299. So that comes to 0.7393. Okay, so now we've got a continuous uniform distribution and which basically means we've got even probability between alpha and beta. If this has a probability density function, and we have beta here and alpha here, it's got to be evenly chanced between those two values and impossible anywhere for it to be anything else. Now, obviously, the mean is the number in between those two. So we have EX, which is equal to 8. But that's got to be the number in between beta and alpha, which is beta plus alpha over 2. So we might write that as a single fraction. Beta plus alpha equals 16. Okay. In part B, it gives us some more information that will get us to work out alpha and beta. So it tells us that the probability that x is less than 13, okay, is equal to 0.7. So let's put that in the diagram again. Okay, so this is 0.7 here. Okay, my 13 and my beta looks very similar. Let's distinguish between those. So that's 13 and beta equals 0.7. Now the thing is, this length from here to here is obviously b minus alpha. And this length from here to here is 13 minus alpha. And the heights are the same, and the total area is equal to 1. So we can say the ratio of these two has got to be equal to 0.7. So we have beta minus alpha, 13 minus alpha, 13 minus alpha over beta minus alpha equals to 0.7. Okay, so we can work with that a bit. So we can write 13 minus alpha is equal to beta 0.7 beta minus alpha. So 13 minus alpha equals 0.7 beta minus 0.7 alpha. And taking the alpha over to the other side, that gives us 0.7 beta is equal to plus 0.3 alpha equals to 13. So it's a simultaneous equation. It's not particularly difficult, but I'm going to do by elimination. Times by 10. And times the other one by 3, so we've got 7 beta plus 3 alpha equals 130, and we've got 3 beta plus 3 alpha equals to 48. So subtracting those two gives us 4 beta equals to 82. So 82 divide 4 equals 20.5. So beta is 20.5 and alpha is therefore equal to 16 minus 20.5, which is minus 4.5. Okay. Part C is variance. There is a formula for variance. There's only one mark here. So there's a formula for variance which is given in the formula book for the continuous random variable. You can use the general formula for variance, but the particular one for the standard for the continuous uniform involves taking away the two values. So we've got 20.5, take away the negative of 4.5 squared all over 12. So that comes to 0.62, 31 over 50 or 0.62. Okay, and D, well, this is just testing us a little bit. If we look at our, now that we know that our values of alpha and beta are minus 4.5 and 20.5, it's just testing that we actually know that the probability that X lies between 5 and 35 is exactly the same as the probability that X lies between 5 and 20.5. Because it can't be above 20.5. So in a similar kind of way to what we've worked before, we're looking at the probability of it being 5 here between these two. So we're comparing this length here to this length here. The length from here to here is 25. So that's, and the length from here to here is 20.5. Take away 5 over 25. So that's 15.5 over 25, which is equal to 31 over 50. Okay, that's that question done. Let's have a look at the next question 3. So it's Poisson distribution, and the first bit's just a standard question where it's asking for the conditions where it can be, Poisson can be approximated using the normal distribution. And hopefully we know the answer to that. Lambda, the mean, must be large. Apparently, greater than 10 is a good thing to go on. So, mean must be large. Obviously, the larger the larger it is, the more accurate the approximation is. Okay, part B. Now we've got some standard stuff. The number of reported first aid incidents per week at an airport has a Poisson distribution with mean 3.5. Find the modal number. Well, I suppose that is a bit unusual. The modal means the most frequent. It's as well to know our shape of our Poisson. It can never go kind of back up again once it starts going down. Basically, it reaches a peak. It might reach a peak right at 0, but it never kind of once it's reached its peak, it goes down again. Now, apparently, I didn't know this. I've got to be honest. According to the mark scheme, the modal number will always be the smallest, the smallest number after below lambda. So the modal will be 3 apparently. So if lambda were equal to 7.5, then the mode would be 7. Okay, I'm not sure what it is if the mode is 7, but anyway, that doesn't matter. Apparently, the mode will always be the next lowest whole number below the mean, apparently. But I'm not going to do it that way because I didn't even know it myself. So it seems a bit perhaps cheating to do that, but it might be worth knowing. What we do know is it's going to be around about 3. So what we really need to do is find that point where it starts to peak, because if we find one lower and then one higher, then we know that that we're kind of okay. So for example, if we find a probability that x equals 2, that is going to be e to the, I'm going to use the formula rather than tables, e to the minus 3.5 times by 3.5 squared over 2 factorial, which comes to 0.184 or 185 approximately. And then the probability that x equals to 3 is e to the minus 3.5 cubed over 3 factorial, and that comes to 0.2158. And then if we find a probability that x equals to 4, I say this might be a slightly long way around, but in the absence of any further knowledge, this will work. That's 3.5 to the power of 4 and 4 factorial, and that comes to 0.189. So the mode is 3. It does say explain your answer. It's probably, hopefully that's enough for 2 marks. We've done quite a bit of work, but the mode is 3 since both numbers either side, probabilities either side are less than this. So that must get us a mark. I've probably gone a bit over the top there, but anyway, that's it. Part B. Then part C, they've changed, this is a kind of thing that they do, they've changed the actual time period. So for part C, the random variable x is the number in 2 weeks, and we're told the number in per week is 3.5, so we've got Poisson 7. So first thing is to find a probability that x is greater than 5. That's the same as the probability for it to be greater than 5. It's got to be greater than or equal to 6. We'll use our tables for this. That's 1 minus the probability that it's less than or equal to 5. In other words, 0, 1, 2, 3, 4, 5, taking away those probabilities. And we can find those numbers on the table. So that's 0.3007. So let's go back to the tables and put that in. There's 1 minus 0.3007, which is 0.6993. Okay, question D. So we've got a conditional probability. They seem to have liked these in the last few years, a few papers I've done. It says, given that there were exactly 6 reported first aid events in a 2-week period, find a probability that exactly 4 were reported in the first week. So there's a lot to think about here. I'm going to actually set it up so that, to try and get our symbols right and try and simplify it a bit. Let's say let A be the event that 6 reported first aid incidents happen in 2 weeks. Okay, and let B be the let's make that, no, we can keep it as it is, but I probably should have made my letters the other way around. It doesn't really matter. Then we can say let B be the event that exactly 4 were reported in the first week. Okay, and the probability we require, it's asking for, given that the 6 reported first aid happened in the 2 weeks, find a probability that exactly 4 were reported in the first week. So we know that A has happened. What is the probability if A happens, B happens? You can see why I might have preferred to label them the other way around, but it doesn't matter. So using the law of conditional probability, or the multiplication law, that's B intersection A divided by PA. Okay, so that's just kind of how we're going to tackle this problem. Now PA will be easy to work out, but then PB intersection A will require a little bit of thought. Let's write down these separately. So PA equals to, now this is the one that occurs over a 2-week period, so we've got that where with lambda equals to 7 here. That gives us e to the minus 7, 7 to the power of 6 over 6 factorial. Okay, that equals to, of course, let's put the value of 7 in for lambda. I'm going to store the number on the calculator just in case I need it, 0.149. I'm not sure if I'm going to be working with exact here or not, but so I'll give myself the option. I've stored it in the calculator. It's approximately 0.149, but we'd never use that rounded number in the question. Right, so that's the top half of this fraction. Now the bottom, let's think about how we work that out. That means that both happen. That means that both B occurs. In other words, that we know that 6 have occurred in 2 weeks, and A occurs, that 4 happen in the first week. Well, the only way that that can happen is if, first of all, B occurs, but also, sorry, first of all, A occurs, that let's get this right. First of all, we want it that we've got the probability that B occurs, which is 4 happening in the first week. So that's e to the minus 3.5 times by 4 to the, so 3.5 to the 4 divided by 4 factorial. So that's the probability that B occurs. But what we need is also that A must occur. Well, the only way that can happen is if in the second week, 1 week period, with lambda being equal to 3.5 in both of those cases, that 2 occurrences happen in the second week. So that will be, so that's 2 occurrences, e to the minus 3.5, because we're just looking at a 1 week period, 3.5 squared, because we've got 2 apparent, we need 2 occurrences in the second week in order to have 6 overall. So that's the probability that 2 occurrences happen in the second week. That comes to, put into calculator, 0.0349. It's not exactly, obviously it's more, I've stored that on my calculator using the memory facility of my calculator. So the required probability is going to be equal to, well, what I did is put the numbers in the calculator like this, of a 0.149. Something happened. They actually get the calculator, kind of surprisingly at first, gave me the exact fraction, which was 15 out of 64, because I didn't round the numbers in any of the work. And then that kind of led me to think, oh, could I have done it without a calculator, which of course we could. S2 is a calculator paper, so wouldn't be necessarily the best use of our time, but did lead me to think, how would it be done without a calculator, if that's the case. Those who know me, I'm an old boy, so come from an age where calculators were not allowed in exams, so that's all, the top bit is all that bit divided by 4 factorial, 2 factorial, and the bottom bit is e to the minus 7 to the power 6 over 6 factorial. And what you actually see is that using the rule of indices is that the e bit actually cancels. So that, because that's e to the minus 7, cancels with that. So you could see how with a bit of work, I'm not going to do it, but it could be done without a calculator with a bit of work. But anyway, using the memory, I would recommend on a calculator give us a precise fraction. The mark scheme does allow anything which rounds to 0.234. Okay. Anything which rounds to 0.234. Okay. Took a little while for those 4 marks, but I did think it required a bit of thought. Okay, so let's go back to the question. We haven't finished with it yet. There's something about a normal approximation. So just pasting it in there to remind us what it was. It's going to be a little bit more standard fare for our 6 marks. It says using a suitable approximation. Well, there is only one approximation that we know for the Poisson. Remember the rate, the 1 week rate, feels a while ago now, was lambda equals 3.5. So we want a 40 to multiply that by 40. So we're looking at Poisson with 40 times 3.5. So that's Poisson 140. Okay, that means we can use a normal approximation. Let's call it Y. As an approximation for it with mean 140 and standard deviation the square root of 140. Okay, so we are being asked for the probability there will be at least 120 reported first aid incidences. So we want the probability that X will be greater than or equal to at least 120. Now we need to apply a continuity correction when we change that to the Y, because we go back from the, so if we draw it on a number line, if 120 is there, always extend the number line backwards, 0.5, so long as we have a non-strict inequality there. So that's 19.5. Okay, so that tells us what we need to work out is a probability that Z is greater than, well, not 119.5 obviously, 119.5, take away 140 over the square root of 140. Okay, when I work that out, that gives me the probability that Z is greater than minus 1.7325 and a load of other stuff. I'm going to use the tables here. I'm going to draw the diagram. We want the probability that it's more than this number here. Oh dear. This is for our Z thing here. We want the probability that it's more than this number, and we've got a negative, so it's the left hand side of this. Okay, so we want that, but that's obviously exactly the same as, by symmetry, this. So that's the same as the probability that Z is less than 1.7, let's round it to 1.73 approximately. Same thing, so we can just go to our normal tables and find a number 1.73 from there. So we're looking at our normal distribution tables, 1.73, and looking at the relevant number 0.9582. 0.9582. You say more standard than the previous question, and see that kind of thing quite a lot. Right, so question 4. Question 4 is a discrete continuous random variable question. Finding the mean, for which we know a formula, which is in the formula book. The actual formula goes something like this for the mean. I'll write them out, they're in the formula book. Ex is equal to the sigma from infinity to minus infinity of x, fx, dx. And the one for Rx, the variance, is infinity to minus infinity x squared fx dx minus ex squared, so we're squaring that one in there to find the variance. So we're just applying those formulas to this particular case. So here's the PDF, and our range is between 4 and 0. So that's 4 and 0 for this particular function, where it is taking values for of x, 3/64 x squared 4 minus x dx. Let's tidy that up a bit before we integrate. That equals 2, let's take the constant outside, 3/64 between 4 and 0, multiplying that out, we've got an x squared and a 4, so that's 4x to the 4, no, x cubed, and then we've got an x squared and an x, and that is x to the 4 dx, and that comes to, let's put the 3 out, 64 outside, x to the 4 minus 1/5 x to the 5 from 4 to 0, so that comes to 3/64 4 to the power 4 minus 1/5 4 times 4 cubed, and that comes to 2.4. So, and going back to the question, don't leave it there, because it says the mean number of hours has a component, the mean number of hours, and it talks about thousands of hours. So the mean number of hours is 2,400 hours. Okay, that's part A done. Let's go on to part B. So part B wants the standard deviation, which is the variance formula we're going to use. So the standard deviation squared is variance of x, so we don't have to times by 2,000 this time. So that's integral of, we're using this, 4 to 0 x squared fx dx, take away the mean squared, which is 2.4 squared. So that's equal to, we can take the 3 out to 64 out this time, and then we've got an x squared with it this time, so the powers are going to be 1 raised from our expression that we had before. So that's 4x to the 4, take away x to the 5 dx from 4 to 0, minus the 2.4 squared. So that will equal to 3 over 64. This integrated, which comes to 4 over 5, x to the 5, minus 1 over 6, x to the 6. From 4 to 0, take away 2.4 squared. So that equals to 3 over 64. 4/5 of 4 to the power of 5. Take away 1/6 of 4 to the power of 6. The zero limit will come to 0. Take away 2.4 squared. And that equals to 0.64, but the standard deviation is the square root of that. So that's 0.8. Okay, so fairly standard marks to be gained there. When we know what we're doing, we really have to take care to get the marks because it's just a case of integrating. Okay, nearly done with this question, but there's just a bit of kind of wordy stuff at the end. It's given us a picture of the function so that we don't have to sketch it. So it's made, I suppose if they were to make it more difficult, they would have got you to sketch it or to actually comment on the function itself and why it might not be realistic, but they've been nice. They've only given 1 mark to it, but then it'd been nice, they've sketched it. Why is this unreasonable? Well, this is about, we go back context, it's about the time in hours of a certain electrical component. Is it really likely that it's going to just suddenly stop at 4 like that? That just seems unlikely. You'd expect it to be tailing off more, really, kind of going that way. It's so suddenly before is the lifetime is unlikely. So let's write something like that. Yeah, some would last longer, surely. It just seems very intuitive. And really to sketch one, I mean, we're happy with the mode being like that. It's not, doesn't have to differ in terms of it, the kind of skewness of the thing. It could be easily coming like this. It doesn't really matter this side, but it's more, we want almost asymptotic, certainly curving down that way on and going beyond 4 if we mark 4 there. Okay, so that's that question done. Let's now go on to question 5. Okay, question 5. It may seem initially a bit confusing here because we've got a Poisson. Here's clearly the word rate. Talks about something occurring at a particular rate over a certain area. But then you start talking about 12 pieces and we're thinking binomial. Well, in fact, what we've got is we've got a binomial on top of a Poisson. So first of all, the rate now is 15 meters squared, and we know that it's 5 meters squared we're given per 2. So the value of lambda is equal to 6, 2 times 3. So that's per 15 meters squared. So we want to find the probability that one of them, let's do that first, at most, so sample of one sample has at most 7. So let's write the distribution. X is Poisson 6, and we want to find a probability that X is at most 7. That means less than or equal to 7. So that number, the inequality is in the direction we want to just read directly from the tables. So Poisson 6, less than or equal to 7, 0.7400, we can see here. So that's the probability that one single piece of cloth has at most 7 defects, but we've got 12 of these, so that's where the binomial bit comes in. So if we let y be equal to the binomial 12, 0.7440, and now we're being asked for the probability that exactly half of them, well, exactly half of 12 is 6. So we're being asked for the probability that y equals 6. So using the binomial, that's 12C6 of 6 times there being exactly half, and 6 times where that is not the case, 1 minus that, which is 0.2560, which is 6, and that equals to 0.0441. Okay, so we've got some hypothesis testing for part B. It says a factory introduces a new procedure to manufacture the cloth. After the introduction of this new procedure, the manager takes a random sample of 25 meters squared of cloth from the next batch produced to test if there has been any change. It's key because it's highlighting two-tailed test in the rate of defects. Write down the suitable hypothesis. Well, that's just writing down the H0 is that lambda equals to, I'm going to write 10. There is some flexibility, per, I'm regarding lambda per the 25 meters squared, and or not equal to 10 because it's a two-tailed test. This is lambda represents, in this case, the rate of occurrences per 25 meters squared. But it doesn't have to be per 25 meters squared, so long as we make sure that we test lambda in our lambda equals 10 in our, when we look for the values and find our critical region. We could equally say 2 per the 5 meters squared which we were given, or even 0.4, which would be per meter squared. Okay, so long as so long as we write the values of lambda that it is, that's what the mark scheme indicates anyway. So that's the first part. That's all we need for the hypothesis, setting up a suitable hypothesis test. Now, the test statistics. Those of you who do S3 will be more familiar with the term, although it is mentioned in S2 and you are expected to know what we mean by it in this context. It comes up in S3 on standardized and normal, testing on samples and things like that of normal distribution, all that. The test statistic here is simply whatever the number of defects is per 25 meters squared. So it's whatever the value of the kind of sample we take, but we need to write it in context. So it is the number of defects observed in 25 meters squared sample of cloth. Okay, and then the third part, the critical region in this context, is again we need to write in context, so it will be the set of values or the range of values for the number of defects in 25 meters squared of cloth for which we would reject H0. That's what you can't put right general statements about what it says. Explain what is meant by for this test, and that's what that's absolutely key. So you have to give context. Right, part C is to actually write this, work out what the critical region is. And as I mentioned earlier, when we were finding the critical region, we've got the sample we've got is 25 meters squared, so we need to be testing for lambda 10. However we write the hypothesis, we write lambda 10. So we can, and we've been instructed to make sure, as we would do even if they didn't say that, to be honest, each tell is less than 2.5%. You will see other questions where it allows you to be as close to 2.5%. But even if it didn't say this, this is what we would do. We have to go below our significance level. So we're looking for critical region, and we're looking for 5%, 2.5%, below 2.5% either side with Poisson 10. Okay, so let's go to the tables and have a look. So looking at Poisson 10, the lower tail is always easier. The first one that falls below the significance level is that, so we've got 3. This one here would be above. Okay, had it asked for as close to, then of course we would have chosen that one. But we're doing the normal thing, gone below, so it's that one. A little bit more problematic writing. I sometimes think it's cautious to write down both of the values, which seem to go either side of 0.250 here. And if it doesn't work out, you can see which one it is. 0.730 gives us a value of 16. It's less than or equal to 16. And 0.2857, because we're basically taking away, we're looking at what we're interested in is the difference between this number and 1, and where it falls below 0.025. It looks like it's this one, to be honest, but let's go back to the main script and write what we just found out down. So clearly we can see that this one is the first one that goes below for the lower tail, so that we're discounting that one. Now looking at the upper tail, we have 1 minus the probability that x is greater than or equal to 17 equal to 0.9730. And that gives us a probability that x is greater than or equal to 17. But the thing is, it actually lies below, above that tolerance level at 0.0270. And here we have 1 minus probability that x is greater than or equal to 18 for this one, equal to 0.9857. So that gives me the probability that x is greater than or equal to 18 equals to 0.0143. So clearly we're not interested in this one, and we want this one for our critical region. Now I do get asked students, do you need to write both possibilities here? And the short answer is no. I'm doing it partly to demonstrate, and you might if you want to, just to be confident, because it is important. It's the first one that's below. So I'm doing it here to demonstrate that we're basically eliminating the 17 because that's gone above 2.5%, and this one's below. But you can, if you wish, so long as you are careful and you are correct. That's a big thing to say, of course. You can, if you wish, just write these down and then write your critical region. So the critical region is x is less than or equal to 3, together with x is greater than or equal to 18. Now for the pure mathematicians amongst you, you can say that x is a positive integer because obviously it's a discrete, but that's not necessary. But well, the mark scheme doesn't indicate that that's what we're looking for. Okay, part D is almost a bonus mark here. The actual significance level is just these numbers added together. So adding those two numbers together, that one there and that one there. So the actual significance, because it's discrete, when we've gone below the thing, that sometimes means the actual significance level of those values is actually somewhat tighter, or maybe than the original intended significance level. So that's 0.0103 plus 0.0143, which is equal to 2.46%. Okay, so that's that question done. Let's go on now to question 6. So in question 6, we've got another significance test, and we have a binomial originally, but we're going to need to use an approximation. So the first thing here is that because the probability is so high, it might be better to think of it the other way around. So I'm going to let x be x equal to 750.04, which is the number that do not germinate. Okay, and we are being asked to use a suitable approximation. Now, Poisson this approximates to Poisson because P is small and N is large. So a Poisson with 75 times 0.04, so Poisson 3. Okay, so that's what we're going to use to test, Poisson 3. Now, we're given the value of a statistic, so 66 germinated. That means that 75 minus 66, which is 9, did not germinate. So let's set up our hypothesis now. Again, there's flexibility here. We can write it in terms of our original 96%, but I'm going to write that P equals to 0.04, or P1 is, and now the test here is one-tailed because of the word we have here, overstating. So in other words, exaggerating the number of bean seeds germinated. So if we think that that's exaggerated, then we actually think the number that fail would be greater than 0.04 to germinate. Okay, you might prefer, and it was maybe in some ways it's perhaps a purer way of going about it, to write P 0.96 and H1 0.96, and it's less than 0.96, which is also obviously equivalent and acceptable as an answer. I tend to use this because it's closer to what we're actually testing when we come to it, but in fact we're using Poisson anyway. So we're going to say, and we've got 9 as the value of our test statistic. So we've got probability that x is greater than or equal to 9, conditional on p equal to 0.04, is it's exactly equal to 1 minus the probability that x is less than or equal to 8. And we will be able to find that number in the tables. So it's Poisson 3 we're looking for. And we're going to have less than or equal to 8, that's 0.09962. So that's 1 minus 0.9962, which is equal to 0.0038, which is less than 1%. So that means we reject H0. Okay, we haven't got the final mark yet, but we're rejecting H0. Let's go back and put it in context. First of all, they've kind of reversed the logic a little bit here. The seed producer is claiming that 96% of the bean seeds are germinated, and we want to find out whether this is actually not the case. So by rejecting the null hypothesis, it does appear that the producer is overstating the probabilities of beans germinating. Okay, so there is evidence to suggest the producer has exaggerated or overstated. Let's use the words that overstated the percentage of beans of bean seeds that germinate. Okay, last question coming up. Okay, so we're doing PDF question. It's one with 2 different rules to sketch. At this stage, I hope that we can recognize this. This is cubic, so it's going to curve this way. So it's cubic to 2. I've gone a bit too much with the curving there. It's cubic to 2. I suppose the only thing I'd check here is, does the same value, because it is possible, it doesn't, but in this case, to have a PDF like that. So it can be a broken curve for a PDF. CDF not, but a PDF can be a broken curve like that. So it's probably as well to check the value of 2 is the same on these for fx, and it is. They both come to 8 over 20. So it comes up to 8 over or 4 over 5 here. So it's as well to check that. I do tend to find that the curves do come out like that. A little bit strange when it doesn't, but it is theoretically possible. So that's one thing I checked when we looked at it. Okay, so that's our sketch. Clearly from our sketch now, the mode So the mode is equal to 2 because the mode is the highest point. Okay, so we've got, just to recap, this is curved this way because that part is cubic. This is going downwards because this part is linear with negative gradient. And also, I suppose the other thing I should say is that it isn't always the case that it will go to 0, but it does here, because when x is 6, this is 0. So, it could have also been, if we, could also, there's no reason why it wouldn't have done that either. But because of the particular values, it goes to 0 at that point. Okay, so then it says, find a probability that x is greater than 2. Well, you could integrate, but I'm going to work out the area of this triangle, because this length is 4 and this length is 0.8. Apologies, it's obviously 2/5 there. That's half times 2/5. That's not 0.8 either, that's 0.4. Half times 2/5 times 4, and that equals to 4/5, 0.8. Okay. That's part C done. Now we've got to do the integrating to work out, fully specify the CDF, should we say. So let's integrate 1/20. Let's define what we're doing. Between 2 and 0, we have fx is equal to the integral of 1/20 x cubed dx. And that equals to 1/80 x to the 4th plus c. If ever we start off at 0, in these cases, the constant will be 0, because we've got f of 0 equals 0, so that implies c equals 0. Okay, so that's for the case 0 between x is between 0 and 2. So now if we consider the other case, if x is between that and 6, we have fx is equal to the integral of the linear function we have here. So that's 1/10 the integral of 6 minus x dx. So that's 1/10 of 6x minus a half x squared plus c. Now we're going to use the fact that f, with these cases where you have a broken one, I use the upper one to find the constant in this case. So we use the fact that f of 6 equals to 1. So f of 6 equals to 1. So that gives me 1. The value of this is equal to 1/10, 6 times 6, minus a half times 6 squared plus c. That's equal to 1, and this here, that's 36, that's 18, so that's 18/10 plus c, which gives me c is equal to, that's 9/5, so that's minus 8/10, so it's minus 4/5. So now we can fully specify, because we've got our two rules for our functions here. Let's do over here. So fx, well, first of all, if x is less than 0, it's equal to 0 because it accumulates, so it can't, the value can't be less than 0. Then we have this rule, but with c equals to 0, so it's 1/80 x to the 4 with x being between 0 and between 2. Okay, let's keep that in like that. And then we can write this thing here. I'm going to tidy it up a bit. We've got that as, let's do that, 1/10 6x minus half x squared minus 4/5. Just have an overwhelming temptation to come up with a common factor of 1/20. That would double this number here, which is 12x. It would it'd just be minus x squared there, and it would be minus 16 here. Okay, so I can write that as 1/20 12x minus x squared minus 16. Often find when we tidy up like that, and we'll find out later, sometimes it helps having a nice tidy expression later anyway, so it's not worth, but they didn't expect to simplify for the answer here. So that's between x greater than or equal to 2, less than 6, or less than or equal to 6, and 1 if x is greater sorry about that, x is greater than 6. Okay, so that's the part C done, part D done, should I say? I think I've mislabeled these now. That's part D. Part C was this. Part D was that. And the mode seems to have disappeared, but mode equals to 2. Okay. So let's go on to the next part. So I thought we would have seen the back of conditional probability, but it pops up again after question 3. It came up, and here we go again. Now it says, given that Px is less than A and x is greater than 2 equals to 5/8, find the value of A, and then in next part we go on to work out A by putting it into this, because we know what FA is. Right, okay. I'm going to use the rule for conditional probability, stated as also known as the multiplication rule. So if we write that, we can say that PA, let's let that be the probability that x is greater than 2, is going to be times by the probability that x is less than A conditional on x greater than 2. If we multiply those two numbers together, and remember we're given this number, then that gives us the probability that both of these occur. So A and B occur. So if I've written out a slightly confusing way, but it is correct. Okay, but we know what probability of x greater than 2 is. That's 0.8. So that equals to 4/5 times by the 5/8. So that equals to a half. But a lot of, I've just marked some of these, a lot of students thought the answer was a half by multiplying the two together, but that is not what we, have here. What we effectively have here, so as I say, it's written a bit weird, this is the probability that both of them occur, that x is greater than 2 and x is less than A. Well, surely that's just the same as saying x is greater than 2 but less than a. Makes a bit more sense, doesn't it? That equals to half. Right, so that basically means in that's fa from this, that's the probability that f is less than a, that p is less than a, take away the probability, take away f2, the probability that's less than 2 is equal to a half. But we know the probability that it's less than 2. Sorry about some of the kind of glitches that are happening here. I'm probably feeling like I'm getting to the end of this. I think it was quite a tough paper. Grade boundaries didn't appear to reflect this because as much as I might have expected. But the probability that x is greater than 2 is 0.8. So f2 must be equal to 0.2. Okay, so that gives us fa equals to 0.5 plus 0.2, which is equal to 0.7 or 7 over 10. Okay, so that seemed quite a lot of work for 2 marks, but the mark scheme just seems to write it as though somehow we would be able to chunk it together. I must admit, working through it myself, I wasn't able to, and I had to kind of revert back to this conditional probability rule and work like that. Okay, part D, and the final part, and now this is the easy bit now. We want to find the value of a. Let's write it as a then. I just realised I've made a mistake now with what I wrote here. Okay, 12x, I wrote it here, there, and just didn't transcribe it. Okay, so that's 12a minus a squared minus 16 equals to 7 over 10. So that gives me 12a minus a squared minus 16 is equal to 20 times 7 over 10, which is 14. So that gives me a squared minus 12a, and that would be plus 30 equals to 0. Okay. That doesn't factorise. I'm going to complete the square, which I think is an easy method when the value is 1 for the coefficient of a squared and you've got even number here. So it's a minus 6 squared take away 36 plus 30 equals 0. So we have a minus 6 squared equals 6. So a minus 6 squared, now take the square root, so a minus 6 is equal to, now it can't possibly be the positive square root of 6 here, because otherwise we know that a lies between, well, we know it's less than 6, that's the key thing, so we actually want the negative square root for there, so we have a is equal to 6, take away the square root of 6, and that I think comes to, if you want a value for it, 3.55. Just looking at the mark scheme, actually, remember this is a stats paper, it's not a pure maths paper, so don't leave your answer as a third, because I don't think, looking at the scheme, that will get you the mark. Leaving it as a third, you get. So that's it. I hope you found it useful. I'm sorry about the few technical glitches along the way and a few little errors as they cropped up, but we got there in the end, and I hope it's been worthwhile. Thanks. Bye.